Thank you. So we've been talking a lot about AI. One possible definition of AI is that is some self-conscious machine that is as intelligent or more intelligent than humans. And that is what many people think out there about AI. When they read about AI in the news, they're thinking of that super intelligence. I'm going to propose another definition of AI that I think is more helpful for what we're doing here. And that definition is AI is a set of tools for data analysis. The first definition of AI is really not something that we have or are likely to have anytime soon. The second definition of AI, I'm going to claim, is much closer to what we call AI in 2024. And some of the confusion about AI among the media, among the public, has to do with the confusion between these two definitions. When people talk about the extinction of humanity, when they talk about the alignment of values of AI as if AI had any values, they're thinking about definition one. But for most practical matters, we can use definition two to have really a fruitful discussion about AI. I mean, some of the good news here is that, of course, the super intelligent machine is not about to take over the human race. So we can leave that aside. That's not what we are talking about. It's not going to happen anytime soon. We're talking about data analysis here. So if we think of AI, which I put in quotes because it's not real AI, it's this thing that we call AI now, is a set of tools for data analysis. Once we think of that in these terms, then we can have a much more helpful discussion about whether AI is trustworthy or is not trustworthy. In fact, we can focus on the actual concerns that we have rather than some hypothetical concerns that may happen in the future but are now far from our time. So the actual concerns that I will discuss here, things like the performance, things like the data and other resources that are used by AI systems, and the transparency. If we think about data analysis, just think of some possible types of data analysis that you know. Things like multiply two numbers, or resolve a complex equation, or beat humans at chess, etc., etc., etc. There is a complexity. There are some data analysis that are very simple, and others that are not. So there is a scale of complexity. At some point in this scale, we started to refer to this as AI. It's not clear exactly what is AI, what is not AI at some levels of this complexity scale. But the machines that do data analysis sometimes were called automata or electronic brains in the 1950s, very quaint now, or computers or AI systems. Okay. So if we think about AI now, it's clearly a very complex type of data analysis because we have machines now that are doing things that until very recently only humans could do. This is a recent view of different tasks that AI systems do now, and how in some cases they have reached levels of human performance, where there are some things like complex reasoning where they are not, they haven't mastered yet. But clearly, very complex data analysis that we're talking about here. Once we think of AI as a set of tools for data analysis, then we can ask questions like, how is AI different? How is first a set of tools for data analysis. Second, how is AI different from other types of data analysis, and how do those differences make it less or more trustworthy, or what are the concerns that come with that? So this is the framework that I like to use to talk about the trustworthiness of AI. Now, if we can think about what are the elements of any data analysis, at a very, very high level, we can think about three elements. First, we need a learning task. What is that we want to learn from that data analysis? Second, we need some hardware and some software. And third, we need to use resources like data, energy, water. All of that is going to give us a result, a response for our data analysis. So I propose to use this outline to think about AI, about causal AI, and about the trustworthiness of this now. So to design an AI system, we will need a goal. That's our learning task. What is that we want this system to do? We will need to talk about the hardware and about the software. We need to talk about the use of resources, and this is all that we need to produce a response. In these few minutes, I'm going to talk mostly about AI for healthcare research. We just heard by Marcos a talk about finance, and there are many other settings in which we could have this conversation. I will focus on healthcare research, but many of my comments are transportable to other areas too. All right, so this is the setting that I am considering here. We have data. We have lots of data that have been generated as part of routine healthcare. That may be electronic health records, it may be insurance claims. We have that for millions of people over many years. This is very, very high dimensional data. And our goal is to repurpose that data. The data sets were not generated for research, but we're going to repurpose them for research to learn something of interest to improve healthcare, to do a data analysis. And some of the things, some examples in which our group and many other groups have repurposed data for data analysis are things like, well, let's see, what is the comparative effectiveness of the two major mRNA vaccines for COVID, using electronic health records from millions of people in the US, from US veterans, coming up with an answer to that question. Or what is the optimal type of timing of screening of breast cancer for women in the US, also using data from millions of women in the Medicare federal insurance program. That's the type of questions that I am talking about. These are things that are doing now. How can AI help with this type of questions? So can AI do this? Can we use AI to repurpose and analyze data at human level at least? And the answer to that question depends on what our learning task is, on what our goal is. This is a point that I like to make. You have interacted with me before. I think it's a key point, and I think it's a reason where we kind of lost a couple of decades in this by not being very clear about the different learning tasks that for which we can use a particular data analysis. So there are three types of tasks that we can do. Each of them have a different requirements for data, for the methods for analysis, and for subject matter. And the three tasks are: one, we can use data to describe. We can describe, meaning we can provide a quantitative summary of some feature of the world. We can also use data to map inputs to outputs. So we have some features of the world here, some features of the world here, and we establish a mapping. That's also known as pattern recognition. Or we can use data to map inputs to outputs if the world had been different. If the inputs had been different from the inputs that you actually see, what would the outputs be? And that is what we do when we do causal inference. We are comparing how the world would be under some set of inputs versus a different set of inputs, even if those things didn't actually happen. Now, a lot of what machine learning has been for many, many years has been number two. When we are talking about machine learning and about all these models and explainable models, we are mostly talking about number two, not about causal inference, which is very important because number two, which is a key task we need to learn. I mean, if a doctor comes, if a patient comes to my office as a doctor and someone can tell me that this patient has a 77% risk of heart failure in the next year, that's very important. Some model is mapping the inputs, all the medical information for this patient to give me what is the risk of heart failure for that patient in the next year. That's very important. It's not causal. It's not causal inference. It's telling me something is happening. It's not helping me decide what to do. So those are very different things. When we talk about the recommendation, we're talking about number three, but most of what has been done in the field has been two, not causal inference. Okay, so let's say that our goal is description. Well, what do we need for AI to be able to do that? We need a clear specification of the task, like saying, tell me what is the 5-year risk of death in people with a recent diagnosis of cancer. We need the compute. We need the hardware that can do that. We need some set of methods for data analysis, the algorithms that will be able to do that, and we need data plus other resources. It actually turns out that this is easily automated if we have all these things, and we typically do. What about the second task? The second task, when we are now mapping inputs to outputs, well, we also need a clear specification of the task. We need the compute. We need some methods. In this case, could be a machine learning model or deep learning, anything that you think, and we need data and other resources. So let me very quickly walk you through the history of this task. We go back to the 17th century. John Grant in London was doing this. He was using data, in this case were the bills of mortality, and he was repurposing that data for research. He was doing pattern recognition by looking at which factors, for example, age, were associated with more mortality. So he was doing that. As compute, well, he had a human computer who was himself, plus a pen and a pencil. He was using just 2x2 tables and live tables. And that's modeled with 1 parameter or 2 parameters. That's what the 2x2 table is, definitely less than 5 parameters. As data, he was using hundreds or maybe thousands of rows with a few columns. I show you an example there. And as energy, maybe a sandwich. That's what you need for a human computer. Now, if you fast forward to the 20th century, epidemiologists and statisticians are also doing this type of tasks, but now they are using computers with 1 or more CPUs they're using things like a cost model or a logistic model with maybe 10 parameters, 20, definitely less than 100 parameters. And as data, they are now using hundreds of thousands of rows and columns. They have now data on lots of people over long periods of time. Now they need some electricity, but it's kind of trivial. You move forward into the beginning of the 21st century, the compute is now much bigger. Now we have hundreds of thousands of CPUs and GPUs. Now we have neural networks. We had them before, but they didn't really run because we didn't have the compute. So now we have maybe thousands of millions of parameters. The data, again, hundreds of thousands to millions of rows and many, many columns, many things like that, and substantially more electricity. And if you think about the first applications of machine learning by the big tech companies, they were all of these types. They were input, they were mapping inputs to outputs. They were not causal yet. My point here is that this is the same task over the centuries. It is conceptually the same, again, pattern recognition, mapping inputs to outputs. What has changed is the scale. We can do it now much, much bigger than John Ground in the 17th century. We just not see what is the association between age and death. We now look at the association of the pattern between thousands of variables and death, say. Also, we changed the name of this, and the final name that we are using as of 2024 is AI. Okay, what about counterfactual? About the counterfactual contrast of two mappings of what would happen if we intervene and we change the inputs in this way versus if we intervene in that way. Well, that's different from the typical mapping that machine learning does because pattern recognition relies on what is in the data, in the training data. And as Marcos has explained, what happens when we want to estimate what would happen if we were making a decision now, but that decision doesn't correspond exactly what is in the data. Well, then we may have it wrong for the two reasons that he mentioned. Either we have confounders that are not in the data, and therefore we cannot adjust for them. We are never going to get it right. Or we have colliders that are in the data, and in a naive way, we decide to adjust for them, and we also get bias there. And last year at this symposium, I talked in more detail about some examples to healthcare research in which these two problems happen. The main implication of this is that for causal inference, we cannot use pattern recognition only. We have to combine that with some knowledge about the causal structure that has generated our data. We need a causal model. And by a causal model, I mean we need to know something about the objects, about the categories, about their connections. That is something that we can often draw on a causal graph, and that's one particularly efficient way of expressing our causal model in a qualitative way. But this is the main point. We cannot use data only. We also use our causal model. And this causal model comes up under many different names when people talk about common sense, understanding. All these things that we use all the time in the field of AI are different ways of talking about a causal model. So if we want to make causal inferences, we need pattern recognition plus a causal model. And the causal model, this requirement, we can replace it sometimes by experiments. And when we don't have experiments, we need to use knowledge from other people, from other humans. So let me explain this, because if we're going to use AI to make causal inferences, then we need AI to either conduct experiments or to get knowledge from other humans. And those are different routes and have different pros and cons. And so for causal inference, we will need our data that we are going to use for pattern recognition, for creating these mappings from input to output, plus the causal model. It's not just data. That's the point here. In fact, even sometimes that we think what we are doing is not causal, we also need causal knowledge. And let me give you an example of what may happen, because there are many things that we think they're just pattern recognition, but they're not. And this links with the talk on explainable AI that we just heard. So sometimes we can have a model that can work very, very well to map inputs to outputs, but is not helpful. And that is because what may happen is what is known as shortcut learning, that by looking for a model that has maybe a very big R square, we're ended up with a model that doesn't really help, doesn't really help us. And let me give you an example of this. In during the COVID pandemic, there was a study that trained a deep learning model to diagnose COVID-19 from X-rays. So you give me the X-rays, and the model would tell me this person has COVID, this person doesn't have COVID. And that was done with the X-rays for several hospitals. And the deep learning model was very, very good. It could do it very, very well. Except that if you give the model an X-ray from a different hospital that wasn't used for the training, it didn't work. It was giving like a random answer. Why? Well, similar to the example about the dogs and the wolves that we were listening about before, the main problem here was that the X-rays from the hospitals had the name of the hospital on the top. They have a watermark with the name of the hospital. And some hospitals treated COVID patients and some hospitals didn't. So the deep learning model was fantastic. So it was very, very good at detecting hospitals. It wasn't looking at the lungs of the patient. So that is an example in which if we think about what the model was doing, was working very well. It was doing exactly what we said. These are the X-rays, tell me whether the patient has COVID or not. But with a new hospital, with a different name, it didn't work. So even for this type of things, we need some causal knowledge. We need to know whether if we're using a chest X-ray, we really want the model to use things like the lung opacity to make the diagnosis. We don't want the model to use the watermark. Then there are some things like the number of ribs that the model is not going to use because it's the same number of ribs in all the X-rays. But how to distinguish what is useful and what is not useful, that's something that we need to provide to the model. We have to make sure that our deep learning model does not use the name of the hospital. Again, this is a very simple example, but it's an example that shows that we need this causal model, which is the name of the hospital doesn't matter. That's a very simple causal model, and we have to communicate that to our AI system, because the AI system may not know that. Okay, now if we can randomize, then we don't need to worry about the causal model as much, because randomization takes care of that. The problem, of course, is that we cannot use randomization for many causal questions. We can use it for some, and when we can use it now, we don't need our causal model, so great. We just randomly assign people to one or the other. So if we can intervene, we can make better causal inferences about interventions. The problem is that we cannot always do that. Can AI intervene? Can AI conduct experiments? Yes, in some cases. If you think about games, the way AI has become much better than humans at many games, after chess, games much more complex like Go, is by conducting experiments. So we have not only the pattern recognition component, say the deep learning model, but we also have the possibility of running multiple games, hundreds of thousands, millions of games, and AI is learning how to play, what works and what doesn't work, by looking at pattern recognition during all those millions of games. Of course, we cannot play games at random, or the learning would be very slow. We have to be clever about how we design which part of the space we are exploring with each game. And there is a set of tools to do that well, and that's known as reinforcement learning. So when we're doing causal inference for games, which is what we are doing, when we're playing a game, it's all about causal inference. What if I move this piece versus this piece? That is because of a combination of pattern recognition, the deep learning, plus the reinforcement learning. And the reinforcement learning, which is a form of experimentation, is replacing the need for randomized experiments. Okay, so when we can do that, when we have a causal model that we can use to simulate experiments, then we just create our own data. We don't need to look for data. We can simulate the data, and then we can make causal inference. So causal AI, the big successes of causal AI are in fields where we can create our own data. And that data will be correct because we know the rules of the game. That is not going to happen generally, but when we've been able to do that, and that works with game, possibly works very well for protein folding, for many things. When we know the rules of the game, we know the physical laws, the chemistry, we can actually simulate experiments. Now, for more complex problems, this doesn't work because we don't know enough to be able to simulate experiments that are actually correct. So in those cases, we are not going to be able to use reinforcement learning in this way. What we're going to have to do is to use data that we're not using for the training of the model to generate our causal model. And that's something that, let me just give you a quick example. The G formula, which is the most general method for causal inference for complex longitudinal data, has to be combined with a causal model. Maybe some assumptions about confounding or no confounding, and only when we combine the G formula with the correct causal model, we get the right answer. But the G formula needs to model a lot of things. That is the first step of the G formula, and that is a concern because every time that we model, and most people have been using parametric models for that type of thing, there is the possibility of model misspecification. So rather than doing that, we can replace those models by machine learning models like long-term, short-term memory models with an encoder on top of those. And this is research that is now happening at Causal Lab. So it will be it will look something like this. We have the deep learning model up there, the LSTM, and that goes through the decoder and a Monte Carlo simulation. And by doing that, we can show that in relatively simple scenarios, we are doing much better with this AI guided causal inference model than just with the simple models that were used before. But the differences are even bigger when we have complex data. So for complex data that looks more like the data that we expect to find in the real world, this is all based on simulations, we are going to get a much better benefit. Now, how do we humans acquire a causal model when they can't experiment? Well, they learn from other humans, and that is how we all learn many of our causal models. So the next question then in causal AI is whether AI can learn from humans too. And this is where large language models come into the picture. They don't have a built-in model of the world. We think that they don't have it. We don't know for sure, but they may be able to learn from humans. So this is in fact how language models are built. They are used with a lot of input from humans that are looking at what the responding for the model and then helping fine-tune the model. That is what is known as reinforcement learning by human feedback. Of course, this is a very costly component of language model because it is not fully automated. You need hundreds of thousands of humans doing it. We don't know how many because the companies don't tell us, but this is where we get to the final stage as of today of where we are, in which our compute now is hundreds of thousands of CPUs and GPUs. We have a combination of pattern recognition algorithms with human feedback. We have lots of data that is being used there and a lot of energy. In terms of compute, this has been going up for the last years a lot. Only in the last 12 years, we see this increasing compute like never before in history. And also, we are using better methods that lead to a net increase in the compute. And this is all leading, as we have heard this morning, to an arms race between companies. Some of the most recent news that we have about the Microsoft and OpenAI new computer is that it will cost $100 billion. It will be working in 2028, and it will use 5 gigawatts. So 5 gigawatts for a single computer. That's more than 1% of all the electricity that was generated in the US in 2023. Of course, this leads to more recent news like Microsoft buying the entire output of a nuclear plant that will be reopened specifically for this, using tax credits. Now, there are some estimates that say that every time that we generate a 100-word email using ChatGPT, we use as much energy as having 14 light bulbs for 1 hour and half a liter of water for the cooling of the data centers. Now, these are only estimates because the actual info is not provided by the companies. So, when you finish here, back to trustworthy AI. This is a very important thing, and the stakes are high because there are very big societal implications here. If you ask people, do we have all the tools for causal AI? Some people say yes. This is what we should be doing. Look at how far we have gotten with deep learning plus reinforcement learning. We just need to increase the compute more, and we'll get there. And we'll get there to the best how we can go. And there are some people who say, no, actually, this seems like a dead end. It seems like even if we increase the compute more, we are reaching a limit here, and this is not the way or the only way to get there. And that's why we are seeing now how these new models, they also include more of a causal model. When we're talking about chain of thought, we are talking about human experts that label things, we are seeing more and more causal model added to language models. And that's probably why they're working so much better now. The thing is that we don't know for sure because we don't know whether current AI systems have enough of causal model in them or not. Some people say yes, and that's why they can reason. Other people say no, but they can reason anyway. Now, this is a scientific question. I'd like to finish with this message. This is a scientific question. Why can't we answer this question like scientists do? Why cannot use just the standard method? Let's try. And what happens if we try? We can't. Because to use these AI systems, we need immense amounts of data, compute, energy, water. So very few people can do this research. In 2024, in the world today, AI systems are not scientific objects. They are commercial products. And we don't know what's going into them. So there is very little external evaluation of these models. This doesn't work like normal science. We don't know the model size and its structure. We don't know the data they were trained on, the type of amount of human feedback, or the computer architecture and the energy that it uses. Therefore, this has never happened in history before. There is this huge divide between industry and academy. There are a lot of questions that are not answered, but they're not answered by choice. Someone has the answers, but they don't share them. We have people who have the tools to answer the question, but not the incentives, industry. And then we have people who have the incentives to answer the question, but not the tools, academic investigators. So it's not possible to explain why these things work or don't work. And at some point, our societies have to make a decision whether this is a sustainable way of continuing or whether we need more of an open exchange between different parts of society. So this is my last slide. If we want a more trustworthy AI, we need an integration of causal models into the system because that's going to increase trust in the performance. We need the justified use of data, energy, and resources. This is going to increase trust by society. And we need more transparency. This is going to increase trust because this AI system will be subject to an independent scrutiny. So thank you very much.
Thank you, Miguel.